Hello everyone and welcome to Lecture Today. Today we'll be extending some ideas that we've developed for line integrals to the next type of integral that we can do on scalar and vector fields. And the idea is that if line integrals are all about essentially integrating a scalar or a vector field over a curve, the next more complicated type of surface that we can consider, or type of shape that we can consider integrating over, is that of a surface. And this is going to allow us to do a number of different things. The line integral allowed us to define the circulation of a vector field. The surface integral is going to allow us to define the flux of a vector field through a surface, a given surface, or the amount that a given vector field is flowing through a specific surface. It'll also give us a means towards going forward and actually redefining the divergence in a very similar manner to how we redefined the curl using the circulation, but for the divergence we'll use the concept of flux. This is also going to lead to us being able to develop very, very strong integral theorems that generalize the fundamental theorem of calculus, which we've already in some sense seen a little bit of when it comes to integrating the line integral of a conservative vector field. So we'll start off by saying, well, let R of u comma v be the parametric vector equation of some surface S. In which case, S is a mapping from UV space into, so we'll say S is a mapping from some domain in UV space to 3D, because in general, surface is something that's defined in 3D. So we really can think of R of UV as being this, a mapping from some space in a two-dimensional parameter space to three-dimensional space. And the idea is that this is always going to define some sort of surface. So let's take a look here and try and get some sort of picture of what's going on. This is going to be a diagram. So whenever we consider a surface that's parameterized by two separate parameters, u and v, these parameters are going to be coming from some domain D in UV space, and then over in, this is the domain of this surface mapping. And then the range of this surface mapping is going to be some surface in three-dimensional space. Where points on the surface correspond to specific points in UV space. So for instance, if you think of this, you could think of, say, fixing some points in UV space. And the question is, why is this giving us a surface? Let's just think of, fixing several points in UV space. We'll fix U1, U2, and U3. In which case, if we fix U1, this actually gives us a parametric curve. This is the parametric curve R of U1, comma V. We fix U2, we get the curve R of U2, comma V. And if we fix the value U3, we get R of U3, comma V. So for instance, just say for argument's sake that U1, U2, and U3 correspond to these values right here. When we fix them, we get a whole bunch of parameter values of V, which essentially corresponds to, on the surface, three parametric curves. One parametric curve that looks like this, one that looks like this, and then one that looks like this. And similarly, we can consider fixing three separate values of V. Sure enough, what we'll get is we'll get three separate parametric curves, R of U, comma V1, R of U, comma V2, and R of U, comma V3. So fixing these values correspond to a whole number of points in the U direction corresponding to these fixed values. And sure enough, on the surface itself, we'll get a curve here corresponding to V3, and a curve on the surface corresponding to V1, and lastly some curve on the surface corresponding to V1 right here, and the middle one is, say, V3. Right, so the idea here is that this is exactly the idea that you want to have in your head of what a parametric surface is representing. It's essentially a way of describing a surface using parameterization, just like we describe a curve using parameterization with one parameter. Because a curve is, in some sense, a one-dimensional object, a surface is, in some sense, a two-dimensional object, so there should be two free parameters. I'll give you two separate examples, but there are infinitely many examples you can come up with. The first one will be the sphere. And if you remember spherical coordinates from your multivariable calculus class, the parameterization of the sphere in terms of two parameters should be relatively clear. And if you don't remember, it's okay. But I definitely recommend going through and reviewing these. The main idea here being that if we have some sphere and points on the sphere can be described by a number of different ways, but the main way here is by using the angles from the x-axis and the z-axis. Specifically, if in the xy plane, any point on the sphere can be represented by some position vector. And specifically, we actually have two separate coordinates that define points on the sphere. There's a number of different ways of doing this, but if we say call this angle the angle V, and we call the angle out to the point along the x-axis the angle U. Let me just move this y right here to make this a little bit nicer. So that this is the y-axis right here. Any given point in the sphere can be described by U and V. And typically in a multivariable calculus course, you start out by looking at this as theta and phi. So if you go back to your calculus book and you look at spherical coordinates, U and V here are just the theta and phi defined for spherical coordinates. So I can definitely explain where this is coming from if you want to see where spherical coordinates is coming from and kind of review the derivation. But when you go through and you do the trigonometry out for how the x, y, and z coordinate depends on these angles, essentially the formula that you come up with is that x is equal to r cosine of u sine of v. Y is r sine of u sine of v. And z is r cosine of v. And this is in the range for u and v, u between 0 and 2 pi, and v between 0 and pi. If we open up a plot of this, this is exactly what we see. Here you see a plot of this sphere right here, and this is actually the sphere itself. So over the entire range of u and v u from 0 to 2 pi and v from 0 to pi, and that's written right here, and the parameters in x, y, and z are written right here. You see when u equals 0, v equals 0, you get the curve right here. This is the curve, the fixed value of u equals 0. That's the semicircle. Right, so v here on this blue curve goes from 0 to 2 pi, while u is fixed at 0. That's why this color is blue right here. And if you rotate this around for u from 0 to 2 pi, you get every single different part of the sphere along this curve. And then we also have to describe points with the parameter v. So if we go through and change v now, but fixed values of v, but let u be open, you see that what you get is all of the curves going up and down. So then these are circles going up and down the boundary of the sphere. So this, for instance, is v equals 1.2. You get this fixed curve right here. So really, any parametric surface you can just think of as a collection of many curves. infinitely many curves. And this is very clearly showing that for this shape, the sphere. So these are all the fixed values of v on the sphere. And these are all the fixed values of u on the sphere. And thus any point on the sphere can be directly described as, a fixed value of two of these points, or two of these parameters. So for instance, if we look at the parameter when u equals 1.9 and v equals, let's say, 0.9, this is the exact point in the sphere that is being described by this expression. So let's just consider one more example. We can consider the torus. And this came up earlier in one of our previous examples when we were talking about curves, where I mentioned the equations of the torus just briefly. We can think of the torus as a circle that we rotate around the z-axis, say, or a given axis. To obtain a donut-like shape, which we can go through and directly derive the equation of the torus very, very nicely. I'm not going to do that here, but it makes a lot of sense based on the fact that the torus is almost like as a combination of two circles, or a circle of revolution. So the torus can be directly described by the mapping r plus r cosine of u multiplied by sine of v r plus r cosine of u times sine of v. Oops, this first one shouldn't be sine, but it should be cosine of v right here. And the last one is going to be r sine of u. So it's relatively straightforward to take these equations and kind of manipulate them to show that exactly what we're getting here is these two separate circles. Here r is the radius of the larger torus, or radius of the larger circle, and smaller lowercase r is the radius of the smaller circle. It's also important to point out that our range of parameters in our parameter space, u here is from 0 to 2 pi, and v here is from 0 to 2 pi. Not including 2 pi. Same thing up here. This I put less than or equals to, but this should be just less than. Otherwise we get a double mapping. So if we open up our plot, this right here is a plot of the torus. These equations that I just wrote down right here, r plus r cosine u sine v. Yeah, this is cosine v, perfect, sine of v, perfect, and then r sine of u. And we're seeing exactly this is from 0 to 2 pi, 0 to 2 pi, and same thing as for the sphere equation. For different fixed values of our parameter, we're getting exactly fixed curves. The union of all the curves represents this surface. So if you change fixed values of v, you get fixed smaller circles. And if you change values of u, you get fixed larger circles going around the torus. So these are two very nice examples that we'll see will prove useful. So we'll start by first just deriving the formula for the surface area of a given surface, and then show that this actually is something a little bit more general. It can be thought of as something a little bit more general, which is called a surface integral. And this process is very much like it was for the formula for deriving the arc length formula, or that integral for arc length. The main idea is that we're going to end up getting some sort of double integral. But so we partition our domain U into very small pieces. In this case, in this picture, we have 1, 2, 3, 4, 5, 6, 7, 8 pieces along U. We have 1, 2, 3, 4, 5 pieces along V for fixed values of V. So on our surface, this partition is going to correspond to a similar sort of picture where we have this partitioning of the surface into a whole bunch of very small pieces. The main idea for finding an expression for the surface area is trying to get an integral expression here. So if we, say, approximate the surface area on each one of these pieces, right, the exact surface area will be approximated by, say, something that we'll call delta capital S. This piece, say, will correspond to a corresponding piece delta D in our partition, where delta D is equal to delta U times delta V for the partition. And technically we should number this IJ, because we have a certain number of partitions along the x-axis, or along the u-axis and the v-axis here. So we'll call this delta Dij, where this is delta Ui and delta Vj. And the main idea here, if we consider this small patch, is to think of the following. So the actual surface, we'll kind of zoom in on this small patch right here. The actual surface itself maybe is curling up, or is curving up, I should say. And this is on that very small patch, delta Sij, curving up like this. And we're not going to get the exact value of the surface area here because of this curving. But if we go small enough with our partition, we will be able to approximate this, specifically by using, if I have a tangent vector in this direction right here, and a tangent vector in this direction right here at this point, then the parallelogram in 3D that's spanned by these two vectors is an approximation to this this delta Sij. Right, if you kind of think of if this vector right here is the approximate length in this direction, and this tangent vector right here is the approximate length of the surface in this direction, then the value of the area of the parallelogram spanned by these two vectors is approximating the surface here. This picture that I've drawn right here is very exaggerated, but think of these as being infinitesimally small, so very, very, very small. So small that this difference right here is almost non-existent. And this is going to be the key, because we mentioned before is that if I fix values of u and fix values of v, I get a curve, and specifically, right, these curves right here correspond to fixed values of u. So u1, u2, u3, and these curves right here correspond to fixed values of v. So you can say v1, v2, v3. It doesn't take much thought to realize that, well, if I have a fixed value of v1, right, like this curve right here is a fixed value of v1, taking the partial derivative of the position vector for that fixed value of v1 is taking dr partial r partial u at any point is going to give me a vector that's tangent to the curve at that point. And we know that the actual approximation to the length at this point is dr du times delta u. And same thing at this point right here in this direction. This vector right here is dr dv. Maybe make this a little bit bigger so that I can put that in there. Alright, this is just a zoomed in picture of one of these subsections, or one of these subpieces. This is dr dv times delta v. And we know that, so now we can do this for each one of these sections, delta Sij, and what that means then is that delta Sij, or delta Sij is the approximation to the actual surface area of each one of these sections. Delta Sij is going to be equal to the magnitude of the cross product of this vector right here and this vector right here. Specifically, this is at delta ui and delta vj. Same thing here. This is at ij, the corner point ij, and this is at the corner point ij. But so the idea here is that for each one of these pieces of the surface, we have this nice approximation. And this is coming directly from the fact that the magnitude of the cross product of two vectors in three-dimensional space will always be the area of the parallelogram spanned by A and B. This is one of your nice properties from Chapter 6 that we ended up showing and seeing in Chapter 6, all the way back in Chapter 6. So the idea then is that we can take this and take delta S, ij, and re-express it a little bit nicer. I'll say it's the magnitude of dr du cross dr dv. Delta ui, delta vj are both positive, and they'll both come out. They're just scalar values, so they'll come out And I'll omit the dependence on I and j here just to make this short, but remember each one of these is different at each different value of ij. So really we should have an index here. I guess I can put one big, and this is being evaluated at the partition piece ij. And the total expression for the total surface area of our surface S and is approximated by the double summation I from 1 to m, j from 1 to n of each one of these delta Sij's. Because what we're saying is that if this is our total surface S, and we cut the surface up into all of these smaller partitions, and each piece of the partition, the surface area is approximated by this value right here, delta Sij, the total surface area is going to be approximately equal to this double summation. Which, as we know, is equal to now the double summation of the magnitude of dr du across dr dv times delta ui delta vj. And this expression is really, really nice because this is exactly right, the type of Riemann sum, only this is a Riemann sum from, say, a calculus 2 or a calculus 4 class, a multivariable calculus class. But it's specifically saying, and we can prove, I'm not going to get into the proof here because it's more of an advanced topic. But we can prove that the exact value of the surface area is going to be, so we'll call this sum, just for simplification, Sn. Call this sum Sn. It's going to be the limit as and we could, I guess, to make this as simple as possible, we'll keep the partition sizes the same. They don't have to be, but it's the limit as n goes to infinity of this Riemann sum. So as the partitions get smaller and smaller and smaller and smaller, and sure enough, this is exactly equal to then the double integral over the space D, so over the space in our parameter space of the magnitude, and like I said, I'll make this ij just to indicate that this is being evaluated at each sub-piece. But this is exactly equal to the double integral of dr du across dr dv du dv. And what we'll do is we'll actually call this is something special. This is what's called the surface integral, the surface area of some surface S is the surface integral of the constant function 1 over that surface. That's what this is called. We evaluate the surface integral by using the parameterization and transferring this to a double integral over d, where ds, that is sometimes called the surface area element, is the magnitude of the cross product of dr du, which is the tangent vector to the surface in the u direction, with dr dv, tangent vector to the surface in the v direction. So this is why this magnitude is popping up, because the surface is changing as u and v change, in the surface area of that the change in that needs to be taken into account. But we'll end up seeing that this idea of surface integral actually extends to any scalar function or vector function that we want to do the surface integral of over a general surface, which is super important for defining things like the flux of a vector field through a given surface. But for now, we'll just stick with this surface area formula and see if we can do a couple of examples. Probably just do one example that will be familiar to everyone. And this is the idea of the surface area of a sphere. And we'll start with the parametric equations of the sphere, which we talked about before. It's these parametric equations right here. And the first thing that we need is those tangent vectors on the sphere, dr du, dr dv. So to get those, and sometimes a nice simplification is that partial derivatives, dr du, can actually be just written with what's called subscript notation. You have to be careful with this because there's multiple different subscript notations in mathematics. But this does sometimes help simplify what we're writing when we're doing tangent vectors to surfaces. But dr du is the u partial derivative of this, which is going to be negative r sine of u times sine of v. That's the partial derivative of the x component. The partial derivative of the y component, with the u, is going to be r cosine of u sine of v. And the partial derivative of the z component is going to be 0. It doesn't depend on u at all. And then the other tangent vector is dr dv, or rv. And rv is going to be the v partial derivative of this expression. Which is going to be r cosine u cosine v. It's going to be r sine of u sine of v, or cosine of v. And it'll be negative r sine of v. And I mentioned before these are tangent vectors. I'll show that right now, just to kind of give you some visual proof of what's going on here. It's always nice to see pictures illustrating exactly what you're doing for your mathematics. So in this case, Right, this is our sphere with our coordinate curves for fixed values of our ordinates. And if we pop on these tangent vectors right here, we see exactly what we're talking about. So this RV here, right, is for fixed values of v, giving us, where v is that angle from the z-axis. So the derivative of the position vector with respect to v is giving us a vector that's pointing tangent to the curve in the direction of increasing v. Right, so we call that 0 as we increase v. The tangent vector is pointing like that, or tangent to the surface. And likewise, u, if we look at u, we'll do it for a larger fixed value of v, maybe 1.15 right here, a little bit lower, 1.05. The partial derivative ru of the position vector with respect to u is giving us a position vector that's tangent to the surface in the direction of increasing u. And what's interesting here, and I haven't plotted it out, but it's not too bad to plot out, so I'll leave it to you to try and figure out how to plot it out, is to plot out the cross product of these two vectors, which is going to be what's called the normal vector to the surface. Right? At any point on the surface, the cross product of RU and RV is going to be a vector that's exactly normal to the surface. And for the sphere, this is we actually can tell exactly what this is going to be because it's a sphere. So we always know what the normal is going to be. But it is important to practice going through the calculations. Right, so I recommend you go through and actually simplify the calculations down for the sphere. Because if you were to say do it for the ellipse or for any other more complicated shape, this wouldn't be the case. So let's just go through and practice finding this RU cross RV. And this is just going to be the cross product of this vector and this vector. This is the vector that's going to give us our normal vector. That's always normal to the surface. So it'll be this times, well, we cross out this first, it'll be this times this. So it'll be r squared times -1 times cosine of u sine squared of v. And then it'll be -0 times this right here. The next one will be negative times, it's going to be this times this, which is negative times negative, so it's positive r squared sine of u times sine squared of v. And it'll be -0 again because it's 0 times this term right here. And then lastly, it'll be r squared times -1 sine squared of u, is sine times sine, sine of v times cosine of v, so it's sine of v cosine of v, and then it'll be minus r squared cosine squared of u sine of v times cosine of v. So this is exactly that normal vector as a function of u and v. It's going to be negative r squared cosine of u sine squared of v. And we can actually bring the negative r squared of u, negative r squared out, because it's common to each term here. That's negative r squared times cosine of u sine squared of v. It'll be sine of u times sine squared of v. And then lastly, you have sine squared plus cosine squared here, so it'll just be sine of v cosine of v. And so this is it. This is the normal vector, and it's actually going to be what's called the inward normal vector, because it points into the sphere. The outward normal vector is just negative times this inward normal vector. But the idea here is that we don't really care about the direction for now. We will care about it later. But this is going to be RU. It's the magnitude that we're looking for in the integral. The magnitude of this is going to be this squared square root. So it'll just be r squared times the square root of cosine squared u sine to the fourth of v plus sine squared of u sine to the fourth of v plus lastly and we'll just put this in below and just make all of this to the power 1/2 sine squared of v cosine squared of v all to the power 1/2, which greatly simplifies. You can factor out a sine squared of v from each one of these terms to get that this is the square root of sine, or r squared times the square root of sine squared, which is r squared times the absolute value of sine of v. And then what you're left with when you factor out, well, this is cosine squared plus sine squared of u, which is 1. And what you're left with is just sine squared plus cosine squared, which is the square root of 1. This is equal to r squared actually just times sine of v, because v, remember, is between 0 and pi, which means that sine of v is between a lower bound of 0 and an upper bound of 1 in this interval right here. This is why the absolute value of sine v here is the same thing as sine of v, which will be nice when we go through and integrate. And luckily, finding this normal field sometimes is the longest step of the process, because this integral is not super difficult to evaluate. We have that the surface area is equal to the surface integral of 1 ds over the surface S. And this is going to be exactly equal to the integral over d, which is from 0 to pi, 0 to 2 pi of ds, which is the magnitude of the cross product of RV with RU, du dv. So this double integral gives us the formula for the surface area of S. This is going to be the integral from 0 to pi integral from 0 to 2 pi of just r squared times sine of v. And this first integral, the function doesn't depend on u at all. So this first integral is just equal to 2 pi. And we have that this is the same thing then as 2 pi r squared times the integral from 0 to pi of sine of v dv, which is 2 pi times r squared times cosine of v is the negative cosine of v. The antiderivative of sine is negative cosine. This is from pi to 0. So the surface area is equal to 2 pi times r squared times cosine of 0 minus cosine of pi. Cosine of 0 is 1 and cosine of pi is negative 1. So our surface area formula is 2 pi r squared times 2, or 4 pi times r squared. And if you go through and evaluate, if you do a quick Google search for the surface area formula for the sphere, this is exactly what will pop up. It's 4 pi times its radius squared. So this is a very, very powerful tool. We've seen that it's definitely giving us the correct result, which is very, very cool. I would recommend going through and doing a couple different examples just to kind of become okay with the idea of calculating using this formula. But the main idea here is that we're directly going to be able to extend the idea now of line integration to surface integration, to surfaces.